Next topic, recursion, variable size reduction. Not reduced by one. The previous example, every time reduce the size by 1. This one, every time reduce a variable size. We don't know how much is the size, variable size. The example, greatest common divisor example. So we know that greatest common divisor. Okay? But now let's use recursion, because there are many different ways to solve it. Given two non-negative integers, m and n, not both 0. One could be 0, but you cannot have two zeros. 2 0, then their greatest common divisor not defined. Okay? M and n both 0, you cannot define what is the greatest common divisor. Okay? So that's why we do not allow both 0. Find their greatest common divisor, GCD function of these two numbers. Okay? Yeah. The first method, middle school procedure. Yeah, in middle school, so there is commonly used the method, right? Prime factors, right? Yeah. Use that example. So step 1, find the prime factorization of n. Okay? Like that. Okay? Step 2, prime factorization of n. Okay? Yeah. Then all the common prime factors, prime common factor, but you get the the power. You need to get the power, the smaller power of the 2. Okay, so you get this 2 square. Okay? And the 3 common prime factor, 3. Okay, yeah. Then compute the product of all those common prime factors, with the power. Okay, yeah. The answer, you get 12. So this one we do not do recursion. Okay? The prime factors, this method we do not do recursion. Okay, yeah. All right. But here we want to use the recursion to solve this problem. Another nice way to solve it. Okay, yeah. So let's look at the recursion idea. All right. Okay. Recursion idea. Let's study the problem size. What is the problem size? Okay. Yeah. So let's define the problem size. The maximum of these two numbers. Yeah. The maximum. Yeah. We define that as the problem size. Okay. We want to reduce that size. When we do recursion, we want to reduce this size. Okay, all right. How do we reduce the problem size? Okay. We need some property. So remember, we need to explore some property. All right, okay, yeah. A mathematical tool we need to use to get that property. A simple tool, you know it, everyone know it, but you may not be aware of it. Okay? It's called a division algorithm. Do division, you know doing division, right? Integer division. Division algorithm. Okay? That division, we wrap it as an algorithm. Yeah. But everyone knows it. Okay? Given positive integers a and b, b not equal to 0. Let's do division. Okay? Yeah. There exist unique integers q and r. Q means quotient. R means remainder. When you do division, you have quotient and a remainder, right? Integer division. Okay? So let's write that integer division. Remainder should be less than the divisor. B divisor. Okay? Divisor. Okay? Less than the divisor. Okay? Yeah. Otherwise, it's greater or equal to divisor. We can move 1 to the quotient. Okay? We can increase the quotient number. Okay? Yeah. So our formula is this: A equals B times Q. Quotient times divisor, then plus some remainder. That's the division algorithm. So simple. You are familiar with it, but it is very powerful. In number theory, this is a fundamental result. Very powerful. Okay? We use this tool, division algorithm tool, to help us reduce the problem size. Okay. All right. How to do it? How do we reduce the problem size using the division algorithm? Can we assume m greater than 0? Yeah, actually, that's too much assumption. Yeah. Although for simplicity, you may like to assume, but too much assumption. So we may not need that strong assumption. Yeah. Why? Yeah, because we only need the maximum not equal to 0. Right? Maximum not equal to 0. The smaller one could be 0. Okay? The maximum not is 0. The larger one, not 0. Okay? Smaller one, 0. No, GCD is also defined. Okay? Yeah. We also know when m not equal to 0, GCD of m and 0, it is m. Because 0 is a multiple of m, right? Both numbers, they are multiple of m. So that's why the GCD equals m. So we have that number. So we don't worry about the 0 case. One of the numbers is 0. Yeah. So that's why we do not need to assume that. Okay? Yeah, we do not need that. Yeah. All right. So now let's, yeah. Here, yeah, m is A, n is B. Let's do division on them. Yeah. So when we do division, even m is smaller than n, we can still do division, right? Even m smaller than n, we can still do division, quotient equals 0. That m equals that remainder. Yeah, no problem. So that's why we do not exclude. We do not need to restrict ourselves in this case. Okay? We allow n greater than m. More general. More general. Okay? Yeah. All right. After this preparation, then we are ready to reduce the problem size. Okay? Yeah. All right. Our next slide, let's do the reduction, size reduction. Okay. Now, all right. Yeah. So based on this, let's do size reduction. Okay. We want to develop a key property for size reduction. Okay. So what's that? Okay. Our original form. Our goal, we want to find this. Because based on the division algorithm, m can be replaced by nq plus r. Okay? Yeah, they are the same. So let's replace it. Okay? After replace it, now we can see there is an nq term. nq term, multiple of n. This n here and a multiple of n here, nq term. Okay? Yeah. How do we simplify that expression? We need a transformation. Through transformation. Okay? At a critical step, the transformation is important. This is a critical step. Okay? So we need to do some special transformation. What's that? This is the transformation. Okay? M over n. Okay? Let's look at the fraction, m over n. If you do that, because m equals nq plus r, that quotient, when you do that, this is also division, right? Just a different way to write division. Okay? Quotient plus remainder R over N, right? This transformation. When we look at this transformation, you can see the greatest common divisor of these two numbers also equals the greatest common divisor of these two numbers, because the quotient does not impact that greatest common divisor, right? Yeah, integral part, yeah? integer part. So it does not impact the greatest common divisor, right? So that's why they have the same greatest common divisor. This pair and that pair, they have the same greatest common divisor. That's the key property. Key property. Okay? So let's write it here. Okay? We can cross out that term. Okay? Yeah, because that's the quotient part. No impact. Okay? No impact. We can remove it. Okay? After we remove, we can switch the position. Okay? Yeah. Because we want to put a greater one first parameter, smaller one second. Okay? GCD of M comma R. Okay? After this, do we do the reduction? Do we do the size reduction? Okay? Yeah. If initially M greater than N, this time the size becomes a smaller one, right? Size reduction. Okay? It's a variable size reduction because how large is the size reduction? We don't know. Every time it could be different. So it is a variable size reduction. Okay? All right. So with this property, we can reduce to the simplest case. To the simplest case. Then we can solve it. Okay. So you can see, we keep doing this. Yeah? Because the next round, we can do another division algorithm. Okay? This time, R becomes division. If R is not 0, R becomes divisor. If R equals 0, that's easy, right? We have GCD equals that N. Because 0, based on our simple observation, previous slide. So R equals 0, we have the answer. We stop. If R not equal to 0, we can do another division algorithm and reduce the problem size. Okay? Yeah. Here, let's use this simple example to do that. Okay? How do we do the size reduction? Okay? 64, let's do division algorithm. Okay? Multiple 24, 12, then we switch, so we get 24 and 12. Okay? Yeah, switch those two numbers, 24 and 12, remainder, right? Yeah. But 24 is a multiple of 24 is multiple of 12. No, sorry. Yeah. Multiple of 12. Okay? So there, if you eliminate multiple of 12, you get a 0. Remainder is 0. Okay? 12, 0, that's 12. See? That's 12. Okay. All right. So you can see we can run this algorithm easily after we get that key property. Okay. Code implementation. So let's just write a pseudocode. This is a famous Euclid's algorithm. 2,000 years ago, Euclid's algorithm. Very famous. Okay. Yeah. The rule, Euclid algorithm, we reduce recursion. This is recursion. Recursion rule like this. Okay? Base cases, 2 base cases. Okay? But we assume x not equal to 0. Okay? Yeah. Yeah. If y equals 0, that's x. Return x. Okay? Base case. Okay? If x mod y, mod operator, remainder, right? So you're familiar with this operation, modular operation. If the remainder equals 0, that means x is a multiple of y, then you return y. Okay? All right. After those two base cases, you do recursion. This is for the remaining cases. This is the recursion, recursive call, okay? Another GCD call. But this time, when you call it, you reduce the problem size. Okay? So eventually, your problem will become easier and easier, and then finally, you reach one of the base cases, you stop. You find a solution. Okay. All right. So that's the idea. That's the recursion. Variable size recursion. Okay. Yeah. All right. Variable size recursion. Okay. So the code like this. Okay. Both 0 return -1, no solution. Right? Not defined. -1. Okay. Yeah. Y0 x not equal to 0 return x. Okay. Another base case, remainder equals 0, return the divisor. Okay? Then the last case, recursion, recursive call. Okay? See? That's the, in this one, you do not do prime factorization. You do not do prime factorization. So we avoid prime factorization. Right? Because there is one thing, when the integer number is really large, the prime factorization is very difficult. When you have a huge integer number, the prime factorization is extremely difficult. Prime factorization, okay? Extremely difficult. So that's why, but this algorithm still works. Easier than prime factorization. Okay? The prime factorization, super difficult when the n number is very, very large. Okay? All right. Any question? No. No. All right. So we complete this topic.